right, we're going to give this a try and see how it goes. So y'all have requested a couple more examples of finding all rational zeros. So I'm going to give that a shot tonight and see if I can get something up for you for tomorrow. So we are looking to find all rational zeros, that is to fully factor p of x is equal to x to the fourth minus 2x cubed minus 8x squared plus 18x plus, or minus 9, sorry. And we're going to use the same sort of checklist that I did in class the last couple of days. All right, so with a polynomial like this, we are basically left to our own devices to figure out, sort of guess and check wise, what the possible x values are that will give us a 0. One of the ways that we analyze the function to get a little bit better bead on that is to use something called the rational zeros theorem, abbreviated Amy style as RZT. And what RZT does is it takes the factors of our end number and our factors of our leading coefficient, in this case a 1, and we are going to use those to figure out what possible real solutions there are for this polynomial. This is often written as P over Q. Let me get my P in here and my Q in there. Where P is the factors of the last number, known as a constant, and Q is the factors of our leading coefficient. So in this case, our last number is a 9. Factors of a 9 are a positive and negative 1, a positive negative 3, and a positive negative 9. Our leading coefficient is just a 1, so our only option for the denominator is a positive negative 1. This means that the values that we want to check are listed as a positive 1, a negative 1, a positive 3, a negative 3, a positive 9, and a negative 9. This is a 9, Amy. This is a beautiful thing because it takes an infinite list of x values. I don't have to check every number on the number line anymore. I now know that there are 6 possible real values that I can check, which makes my life a whole lot easier compared to having to think about all the fractions that it could be or all the decimals that it could be. So one of the other things that we can do is we can use Descartes' rule of sign. That's another one we wanted to practice this way out. Descartes' rule of sign uses the terms and their signage, the positive, negative values, to analyze whether we'll have a bunch of positive solutions or a bunch of negative solutions, and even whether or not we'll get imaginary solutions. So what we're going to do is we're going to take our original function, which is p of x, and we're just going to mark down our signs. The first term is positive, the second term is negative, the third term is a negative 8x, the fourth term is a positive 18, and the last term is a negative 9. If I look at the signage and what's happening there, you see we switch from positive to negative, and then we switched from negative to positive, and then we switched from positive to a negative. This is a total of 3 sign changes. All right, if I look at p of a negative x, oops, p of a negative x, this is going to give me a negative x to the fourth, means I'll have 4 negatives. That will stay positive. 4 negatives will still be a positive. A negative x to the third means I'll have 3 negatives, and with the one that's already out in front, that will convert this term to a positive term. negative x squared would give me two negatives. That's a positive, and that's a negative out in front. So a positive and a negative means it will remain negative. And if I look at the 18 and put a negative x in there, that will change out the sign on the 18 to negative. And my 9 was already negative. You notice here, I only have one sign change. So that's just going to be one sign change. For Descartes, you will often see a lovely little chart with a positive for the number of positive solutions, a negative for the number of negative solutions, and an I for the number of imaginary or complex solutions. Notice that in this polynomial we had degree 4, which means total we are looking for there to be 4 possible solutions to this polynomial. It should cross the x-axis a total of 4 times. Now, there are a lot of ways around that with multiplicity and all the rest, but I'm looking for 4 possible roots. Because Descartes had a p of x with 3 sign changes, I know there can be as many as 3 positive real roots. If I then have 1 negative real root from p of negative x, that's already a total of 4. So in that case, I would not have any imaginary roots. Now, I could have 2 imaginary roots because they come in conjugate pairs, which means since I have to have 1 negative root, 1 sign change means there will be 1 negative root. That would leave me with 1 positive real root. So this is another option. Descartes tells me the combinations that I could have. I could have 3 positive real roots and 1 negative, or I could have 1 positive, 1 negative, and 2 imaginary. In all cases, it should add up to be 4 along each line. This is helpful when I'm using the remainder theorem. Now I want to use the remainder theorem to check and see which one of these possible 6 options will work to give me a 0. How do I do that? The remainder theorem says, oh, this is so fun to write. The remainder theorem says P of C is either going to be a point on the line, on the graph, or it's going to be a 0. So what do we want to check? Since there are possible 3 positive ones, I'm going to check P of 1. And all that means is I'm going to put 1 into my polynomial. 1 to the 4th is 1. 1 to the 3rd is 1, so that will be a minus 2 times 1. Minus 8, because x squared is 1, plus 18, and then a minus 9. And if I look at all of these, I'll add up my positive numbers. That's a 1 and an 18, so that's a positive 19 for my positives. And then I have a negative 2, a negative 8, and a negative 9. That's going to be minus 19. This is going to give me a 0. That means that 1 is a 0. So 1 is a 0 for sure. It works. All right. I can go ahead and try a 2 or a 3. So I'm going to go ahead and try a 2. So if I put a 2 in, that's 2 to the 4th, that's 16. Minus 2 times 8, so that's going to be a minus 16. Minus 8 times 4, that's going to give me a negative 32. Plus 18 times 2 is a 36. And then minus 9. So I like to add up my positives. 16 plus 36 is 52. Then I have a negative 16 minus 32 more. That's a negative 48. Minus 9 more is a negative 57. That's going to give me a negative 5. So this is not going to be a root. It is still a point. There's a point at 2, -5, but this will not be a root. All right, keeping going. I could have as many as 3 positives, so I'm going to go ahead and check a 3. And if I do P of 3, 3 to the 4th power is 3 times 3 times 3 times 3, or 9 times 9, that's 81, minus 2 times x to the 3rd, that's going to be a 54, x to the 3rd is 27, times 2 is 54, minus 8 times 9, that's going to be a 72, and then I've got plus 18 times 2, that's going to be a 36. Beautiful, minus 9. So this is going to give me, if I do my positives, that's going to be the 81 plus 36, that's going to be a 117. And then if I put together a negative 54, oh shoot, I have an error. That's not going to be 36. Hold on. I did 18 times 2. I need to do 18 times 3. My bad. 18 times 3 is a positive 54. There we go. Then I've got a minus 9. Much better. So then I've got an 81 plus 54, which is 135. That's how I did it. And that's how we find our mistakes, folks. And then I've got a minus 54 minus 72, which is a negative 126. Minus 9 more is a minus 135. All right, so that's also going to give me 0. So 3 is also a 0. Because P of 3 gave me 0, so 3 will also be a 0. Now, at this point, I know I need 4 zeros. I've found 2 of them. So that means when I get to my end result, it's just going to be a quadratic formula. It's going to be degree 2, and I can use quadratic formula on it. So I'm not going to continue on checking. I needed 4, I found 2, that leaves 2, and you can always find the last 2 using quadratic formula. So I'm going to leave it here with this one. Okay, once I know at least enough zeros to get me down to 2, I can use synthetic formula, or synthetic division. So I'm going to use my 1 here, and then I'm going to put in my coefficients of 1, -2, -8, so much fun to write the 8s, positive 18, and a minus 9. I'm going to leave a space for my multiplying and dividing. That was a minus 8, right? And then I'm going to bring the first one down. That's 1. So then what do? We do 1 times 1, which is 1. -2 plus 1, which is a -1. 1 times a -1 is a -1. -8 plus a -1 is a -9. 1 times a -9 is a -9. 18 minus 9 is 9. 1 times 9 is 9. -9 plus 9 is 0. I wanted to get a 0 because I know 1 is a 0, so I'm going to go ahead and use that. Now, using this exact same form, I can go ahead with my next 0, which should be a 3. So I'm just going to choose another color to help me delineate one from the other. And I'm going to put the 3 on the outside, and I'm going to continue down. 1, bring that down. 3 times 1 is 3. -1 plus 3 is 2. 3 times 2 is 6. -9 plus 6 is a -3. 3 times a -3 is a -9. And this gives me a 0. At this point, I know that my P of x is x minus 1, x minus 3, and then this 1, 2, and -3 stands for an x squared plus 2x minus 3. You can either use quadratic formula on it, or you can check to see if it's factorable. I know that this factors into an x plus 3 and an x minus 1. What two numbers multiply to give you a negative 3 and add to give you a positive 2, x minus 3, x minus 1. This means that my p of x my p of x is going to equal, where's my first one? I had an x minus 1. I had an x minus 3. And then I know I need that x plus 3. And that x minus 1. Notice I had 4 factors, and I knew I was going to need 4 total solutions. So what are my solutions? So the zeros, that's the last bit here, my zeros, so hard to write. My zeros are going to be at x equal 1. But look, I've got a second one, so I'll write the 1 again. This 1 has a multiplicity of 2, because there's 2 of them. Then 3. And in order to zero this out, I need a negative 3. So I have fully factored it right here in 5. And I have listed all of the zeros here in 6. Great. Oh Lord, I hope that didn't, let me pause this.